We envision autonomous agents as lifelong learners, systems that don't just solve a problem and stop, but instead reflect on their errors and distill that experience into persistent, reusable skills. The goal is a repository of knowledge that grows more capable and efficient with every new task the agent encounters. But checking if this evolution actually happens is difficult because of how we currently evaluate AI. Most standard benchmarks use isolated, memoryless episodes. An agent is dropped into a task, and the moment it finishes, its memory is wiped completely clean before the next test begins. This static environment is a poor reflection of reality. In a production deployment, an agent doesn't work in a vacuum. It handles a continuous, interrelated stream of financial reports, legal filings, or software bugs, where lessons from one hour directly apply to the next. To bridge this gap, many developers operate under an untested assumption that if an agent is programmed to write its procedural lessons into standalone files on a hard drive, it will naturally build a library of expertise that guarantees improvement. Determining if that theory holds up requires moving past static testing. We have to stress test these agents across dynamic, progressive task streams to see if they can truly consolidate experience into abstract, transferable skills. This is the framework for ContinualSkillBench. It's a diagnostic tool designed specifically to track whether an agent's capability actually evolves over time. The benchmark consists of 500 tasks across 5 real-world domains, including healthcare, law, and mathematics. These aren't random. They are sequenced strictly by difficulty, moving from fundamental building blocks to complex strategic workflows. By analyzing the semantic dependencies of these tasks, researchers found that nearly 70. This suggests that while sequential learning is effective, the ability to reuse knowledge is deeply constrained by the mechanical nature of the specific task domain. The most significant test in this benchmark pitted 2 memory strategies against each other: the standard method of saving explicit skill files to a disk versus pure in-context learning, where the agent simply keeps its recent conversation history in its active window. The data shows an equilibrium. Pure in-context adaptation scored 0.605, matching the 0.602 of an explicit repository. Retaining recent feedback in the active buffer lets agents move fast, avoiding external file retrieval. Explicit files only retain an advantage for tasks demanding rigid, multi-file templates. For the majority of sequential workflows, adapting to the immediate environmental feedback already present in the conversation is just as effective as distilling that experience into a permanent file on a hard drive. While performance may be similar in the short term, looking at the long-term health of an agent's skill repository reveals a massive divergence in how different models handle their memory. Highly capable models, like Codex, demonstrate a consolidated memory. They build a compact library of 205 broad skills and reuse them constantly, averaging over 3.5 calls per skill. They generalize their lessons. Less capable models suffer from a pathology called hyperfragmentation. Their repositories explode into nearly 400 separate files, but the reuse rate collapses. On average, a skill is called less than once, meaning the majority of what the agent saves is never used again. These models lack the capacity to abstract a general workflow. Instead of updating an existing skill, they create brittle, task-specific copies filled with hard-coded paths. They aren't learning, they are just duplicating. Over a long execution horizon, this unchecked bloat floods the catalog with redundant noise. The repository becomes a liability, degrading the agent's retrieval accuracy and slowing down its decision-making. To build agents that can truly survive in the wild, architectures must move beyond simple accumulation. We need semantic deduplication gates that force an agent to refine existing knowledge, rather than creating a new file for every minor variation. Just as important is automated garbage collection, systems that can identify and purge obsolete, single-use skills before they clutter the active memory. Sustainable lifelong autonomy isn't about remembering everything. It's about the architectural capacity to forget the noise and consolidate the signal.